Hello everyone. We will continue chapter 4 with section 5, that is transient control volume analysis. Up until now, especially in the last two sections, we focused on the steady state control volume. Okay? But there is a possibility that the control volume can also be transient. Okay? So if you remember the definition of the transient, it is kind of the opposite of steady. Okay? And a property, if any property changes over time, okay, even if a single property changes over time, then that's basically a transient analysis for at least one property of the system. Actually, I should say the system that you analyze, okay? Which is kind of, as I said, the opposite of the steady state definition. Common examples are in this course, okay, like filling a tank or emptying a tank. So you will see in some of the examples, you have a pipeline, okay, and this pipe is connected to a smaller pipe, okay, like this, through a valve. This is a valve, electronic device, and it is connected to a tank. Let's say a closed tank. So this is going to be referred as a carrier pipe or just a pipeline, okay, and you have the mass that gets into here, okay, and this is a common transit analysis because initially, let's say the level is here, you have M1, okay, and at a later time it's going to be M2, the mass is going to increase, okay. So since mass is accumulating here, at minimum mass changes over time, okay, so maybe I should say dm by dt is not equal to 0. Since mass changes over time, it is not a steady state system. In addition to mass, maybe the temperature changes. If we are adding gas, the pressure changes, okay? So it really depends. So this is a common example, basically filling a tank. Just the opposite is also a transient analysis, like you have a tank, okay, and you have a discharge valve over here, okay. So this means you are basically emptying the tank, okay. So as I said, so if you take the system as such, by the way, and you can consider the system as such, so we are just considering the tank here. Again, at minimum, mass changes over time. So this is emptying a tank. Therefore, it cannot be steady. Is it control volume? Yes, because mass is leaving the system in discharging the tank, or on the left example, mass is entering the system. So it is not control mass system. It's control volume system because mass is inletting, mass is exiting. Okay, entering or exiting. This can be combined. So on one hand, you can fill a tank. On the other side, you can basically empty a tank. That's also a transient one if these flow rates are not equal to each other. Okay? So this is basically the application over here. I hope I am clear with these examples. Let's consider the mass balance for the transient analysis. This is no different than the previous ones, except it's not going to be simplified as before. So the mass balance is dm by dt is equal to m dot in minus m dot out. So at steady state, the left-hand side was going to be 0, but in this case, it's non-zero because it's transient. Therefore, what you do is you multiply both sides with dt, okay, and then integrate it these three terms. The left term, the term on the left hand side becomes m2 minus m1. And this becomes, I did this before actually, you may remember. This becomes the total mass that enters the system. This becomes the total mass that leaves the system. Okay? Here the units are kilograms. They are integrated over time. Here the units are kilograms per second in the rate form. Okay? And this part referred as the change of mass of the system, inside the system. And the ones on the right hand side are the ones that cross the system. Similarly, you can consider the energy balance. In the energy balance, let me write in the most general form, dE by dt q dot plus, let's say, single inlet. So I'm going to not consider the summation term, minus w dot plus m dot out h total out. Okay. So once again, let me remind you these, where E is the energy of the system. It composes of internal energy of the system, kinetic energy of the system, and potential energy within the system boundary, or maybe I should say inside the system boundary. So this is the energy of the system, okay, where H total is the total enthalpy, consists of enthalpy, kinetic energy, and potential energy. This basically is specific energy crossing the system. Okay, so when you check the energy balance, left hand side of the equation is the energy of the system or inside the system boundary, and the ones on the right hand side are the ones that are crossing the system. So similar to the mass balance, multiply all the terms with dt. It becomes q dot dt plus m dot in h total in dt minus w dot dt minus m dot out h total out dt, and integrate all these terms to get the total form. The left hand side becomes delta E, basically E2 minus E1. Okay. The right hand side becomes Q dot, sorry, Q, the total energy that crosses the system boundary through heat transfer. And let me leave this as it is for now. Okay. I have minus work. Instead of power, I have work, and I have the second integral. I leave these integrals as they are because for a reason. The reason is that these terms need to be integrated. Let's say this is A, this is B. Okay? So A and B need to be solved. If the enthalpy in and enthalpy out are not constant. So basically there is a possibility that the enthalpy of the incoming mass or leaving mass changes over time. Okay? Therefore, if they change over time, you need to integrate this one. So for instance, let me scroll up. Let's consider the example on the right side, the discharging part. Okay? So what happens here is it has a particular temperature and pressure. So it has a particular energy, right? Initially, let's say this is at T1 and P1. And let's say you have a gas. Just an example. You write 1. Okay. and it has a gas. As the gas is discharging over here, what's going to happen to its pressure? It's going to change. It's going to decrease, right? And as it decreases, what happens to the energy of the discharging gas? It also changes with time, right? It's going to decrease basically with time because pressure decreases. Therefore, this term over here in B is not going to be constant. It's going to be a function of time. Therefore, if you want to solve this energy balance, you need to know how this enthalpy changes over time so that you can integrate this term and calculate B and then put this into the energy balance. Okay, so this basically means HT in is a function of time and HT out is a function of time as well. It is possible. Okay, so this means these, right, is not constant, means they are function of time. But sometimes they are constant. They don't change over time, especially for the filling. And that is what we call as the uniform flow assumption. The entire idea about uniform flow assumption is that enthalpy in the transit flow is constant. It means it is not changing with time. And to simplify your analysis in this course, assume uniform flow for all the transient control volume problems, not control mass, because all control masses are transient. Okay? Transient control volume problems in this course. Just to simplify your analysis. Okay, in reality, know that it may not be constant. Right? Therefore, if that is the case, the energy balance is going to look like this: E2 minus E1, which is delta E, is equal to Q, which is the total heat transfer, and this A, m dot in m dot in integrate over, let me put it this way. This HT in is independent of time. So you can take this HT in out of this integral, right? Then it becomes the integral of m dot in dt, which is just m in. Okay, so it becomes m in h total in. This is the energy into the system through system boundary. And we have W plus m out h total out within the parentheses. This is the energy out. The same idea. Right. So here all the terms have the unit of energy. So joules, kilojoules, whatever, okay? The unit of energy that we have. Because this is not the rate form, this is the total form. So the unit is energy. Whereas in the rate form, this one, it is kilojoules per second or kilowatts. All the units, all the terms have the unit of power, rate of energy. Just to remind you. Once they are integrated over time, they become joules, kilojoules, or megajoules, gigajoules. We have the common assumption that you know the negligible kinetic and potential energy effects. So if you have that assumption, the total energy becomes the internal energy because you have neglecting the kinetic and potential energies. And the right hand side, the total enthalpy becomes just the enthalpy. When you neglect the kinetic and potential energies. Okay? So, let me summarize what we did in this chapter. And let's say this is section 6. Summary of balances with, just to simplify it, I will just do the kinetic and potential energy effects. And we have three of them. Okay, so maybe I should divide this into 3 as such. Use different. So the first one is going to be control mass, which is always, as I said, transient. The second one is steady state control volume. And the third one is transient control volume. But with transient control volume, I'm going to assume uniform flow assumption. So it means the enthalpy in or enthalpy out is constant. Okay? So transient control volume, it is a typical one is a piston cylinder assembly. So let me put the schematic. Okay, so the piston goes up and down, or left and right in the schematic. This is the system boundary. So you typically have the boundary work. You might also have the heat transfer into the system or not. Okay? A steady state control volume, as an example, let me give you the schematic of a turbine. It can be a compressor, heat exchanger, okay? And you can have the inlet or exit. So let me just say in or out. Okay? And this is, let's say, filling a tank. This can also be, by the way, a piston cylinder assembly. It's not necessarily a constant one. You can have also out, just to generalize. And as I said, it can be a piston cylinder. It's not necessarily a rigid tank. Okay? So, when you write down the mass balance over here, dm by dt is equal to m dot in minus m dot out. Okay? So, let me take this. It didn't get this division, so I'm going to put it both. So this is the conservation of mass, right? And since this is control mass, there is no m dot in, there is no m dot out by definition of control mass, right? Therefore, you can say dm by dt is equal to 0, which means m2 minus m1 is equal to 0, which means it's control mass. m2 is equal to m1, and we call this m. This is why, especially in like chapter 2 or 3, we didn't consider any mass balance, because mass was fixed over there. We didn't need to do any analysis for that purpose. For the control volume steady state, okay, it's at steady state, therefore this part is equal to 0. Okay, then you get m dot in is equal to m dot out. Okay, if you have single inlet, single exit, okay, you can call this as m dot. If you have one inlet, one exit, let's simplify this and get m dot. For the transient control volume, none of the terms disappear. Okay, so again, multiply all the terms with dt, and it's going to be m2 minus m1 is equal to m in minus m out. Again, multiply all the terms with dt, then integrate it, you are going to get this. The energy balance, let me write in full term over here. I already assume we have negligible kinetic and potential energy effects, so I'm going to write down this term, this form. Okay, so this is the energy balance, and let me consider control mass first of all, which is part A. Okay, I will do this work this time. Okay, finally. So I will do the simplifications for control mass. And for control mass, as the name implies, you don't have any m dot in or m dot out. They are both 0, right? And as I did, just multiply all the terms with dt, and then it's going to be, and also apply the mass balance. So it's going to be m u2 minus u1. The left hand side becomes this, okay, and the right hand side becomes q minus w, which you are familiar from chapter 2. Okay, it comes from this. For the control volume at steady state, the left hand side is going to be 0, because of the steady state operation, right? And both m dots in and m dot out are m dots, single in, single exit. Therefore, from here we can have 0, or I can write it this way. 0 is equal to q dot minus w dot plus m dot h in minus h out. It becomes like this. Okay? And finally, transient control volume. Then you have no simplification. So this is kind of the most complicated one among these three. And as I said earlier, we start with the simplest one, that was the control mass. With this chapter, we add the control volume, both steady state and transient. So we make things more complicated. So in this case, when you again multiply all the terms with dt, do the integration, it's going to be m2u2 minus m1u1, that is going to be the left hand side, is equal to q plus m in h in minus w minus m out h out. Or I can make plus and put in the common parenthesis. This is possible, right? So this is basically the summary of chapter 4 as well as chapter 2 and 3, for if you consider the control mass system as well, right? So we have concluded chapter 4. Let me know if you have any questions as usual. and take care, stay safe. Until next time, bye bye.